Why do deadlocks occur in real-world systems? Have you ever wondered why your computer freezes when running multiple applications? This frustrating situation can often be traced back to a phenomenon known as a deadlock. So, why do deadlocks happen in real-world systems? Let's break it down in simple terms. Deadlocks primarily occur when multiple processes or tasks compete for shared resources. Imagine two people trying to use the same printer at the same time. Each person is holding onto their own documents while waiting for the printer to become available. This creates a standstill where neither can proceed. For a deadlock to happen, specific conditions must be met at the same time. First, there is mutual exclusion. This means at least one resource is non-shareable. For example, a printer can only serve one print job at a time. Next, we have hold and wait. This condition occurs when processes hold onto resources they already have while waiting for additional resources. So, if a process is using a file but needs another file to continue, it won't releases the first file. The third condition is no preemption. This means that resources cannot be forcibly taken from a process. A process must voluntarily releases the resources it holds. Finally, there is circular wait. This is where a chain of processes exists, each waiting for a resource held by the next process in the chain. This loop creates a deadlock situation where no process can move forward. In practical systems, these conditions often arise. Tasks may need exclusive access to resources like files, memory, or hardware devices. When multiple tasks request overlapping sets of resources without proper coordination, deadlocks can occur. The consequences of deadlocks can be serious. They can lead to system crashes, data corruption, and performance issues. In critical systems, like automotive control units or medical devices, a deadlock could even pose safety risks. For instance, if an airbag control system experiences a deadlock, it might prevent the airbag from deploying in an accident. To tackle deadlocks, understanding their causes is essential. There are several techniques for managing them. One approach is to use resource allocation strategies that prevent circular wait by enforcing a strict order of resource acquisition. Another method involves deadlock detection algorithms. These algorithms monitor resource usage and can identify deadlocks when they occur. Recovery methods can also be employed, such as terminating or rolling back processes to break the deadlock. Lastly, avoidance strategies can dynamically check resource requests to ensure they do not lead to deadlocks. Mastering these concepts is key for effectively debugging and fixing concurrency bugs related to deadlocks. By understanding why deadlocks occur, you can design systems that maintain reliability and performance.